Welcome to the second video of your Monte-Carlo Simulation and Modeling series, in which I will introduce the beta distribution. I will explain what it is about, discuss the formula including its parameters, and how we can implement it using Microsoft Excel. Let's start with number 1. What is the beta distribution about? By now, you are already familiar with various probability distributions, such as the binomial, the geometric, the exponential, or the normal distribution. All these distributions establish a connection between values and their associated probabilities of occurrence. The beta distribution serves the exact same purpose. However, what sets it apart is its unique domain of definition, which is confined to the closed interval between 0 and 1. With that, the beta distribution offers a framework for modeling the likelihood of anything around percentages, shares, or likelihoods, and is therefore often referred to as the probability of probabilities. For example, we might be interested in understanding the likelihood of a person choosing a specific brand, the probability of a machine producing a defective item, or a business partner's likelihood of accepting a contract proposal. Let's explore that last example a bit more for a better understanding. Imagine we have sent a business partner a total of 10 proposals, of which he has accepted 6 and rejected 4. Naturally, we would conclude that this partner's acceptance probability is 0.6. We could use that value and the binomial distribution and calculate, for example, how likely it is that such a partner out of 10 proposals would accept 0, 1, 2, and so on up to 10 proposals. Let's do that real quick. So, n is 10 and theta is 0.6. I can use the formula binom dist and these two parameters to calculate the desired probability, as we have done many times before. We find that 6 acceptances are most likely, but 5 or 7 or even 4 or 8 are fairly possible too. However, this is all somewhat theoretical because we know that a partner has accepted 6, not 4, 5, 7 or 8. And we are aware that our 0.6 is just an estimate based on a total of 10 observations. In fact, we should turn the question around and ask, how likely is the acceptance of 6 out of 10 proposals given a certain acceptance probability? So, what do I mean by that? Let me repeat the calculation, but this time experiment with different acceptance probabilities theta and find out how likely each of them would make a total of 6 acceptances. This can also be done using the function binom dist, but this time I fix the number of successes to 6 out of 10, whereas I take the acceptance probabilities from column D. We find that an acceptance probability of 0 is impossible, as it would clearly contradict our observation of 6 acceptances. Similarly, an acceptance probability of 1 is not possible either, because 100% implies that every single proposal would have been accepted, not just 6. The most likely acceptance probability aligns with 0.6, but we notice that values like 0.5 or 0.7 also result in probabilities that are not too far off. And what we've done here is, in essence, what the beta distribution does. It explores the probability of probabilities, but not merely for a limited set of a few examples, like I've illustrated, but rather for the entire spectrum spanning from 0 to 1. Let's delve into the formula. In the formula, I've kept theta as argument to remind us that the acceptance probability is the independent variable, and we want to calculate how likely each acceptance probability is. However, in statistics books, you'll find the theta replaced with an x, as in all other distribution models. But regardless, it still refers to the domain of definition from the horizontal axis of this chart. I also prefer to keep the theta as it helps us recognize some resemblance to the binomial distribution within these components. The parameters are alpha and beta, and we find them in the exponents over here, as well as in this term in the denominator. The denominator term is known as the beta function and actually just holds a fixed value for a given alpha and beta. It ensures that the beta distribution is in fact a probability density function. In other words, it makes sure the integral from 0 to 1 equals 100%. For our purposes, we actually do not need to worry about the beta function too much, because there is a neat Microsoft Excel implementation which takes care of it automatically. I will show that in a minute. But before we get there, let's take a look at the lowercase alpha and beta values, the parameters. This can be swift as we can leverage the connection to the binomial distribution. Consider this. If we interpret x, which was 6 proposal acceptances in our example, as being equivalent to alpha minus 1, it follows that alpha equals x plus 1. Similarly, if we relate n minus x to beta minus 1, then beta equates to n minus x plus 1. In practice, this means that if we have, for instance, a total of 10 observations with 6 successes, or hits to use a broader term, and 4 failures, or misses, we define alpha as 7 and beta as 5. For a scenario involving 50 observations, where 35 are hits and 15 are misses, we would designate alpha as 36 and beta as 16. Now, let's explore how Microsoft Excel can assist us in handling the beta distribution. I'll revisit the example involving 10 observations with 6 hits and 4 misses, which translates into alpha being 7 and beta being 5. The formula to use here is beta dist, which takes arguments like x, which again I have denoted as theta, i.e. the various hit probabilities, alpha, beta, and a cumulative parameter, either true or false, a concept familiar to you from other models. For the density function, it is 0. At this point, I'll disregard the capital A and B, close the parenthesis, and press Enter. I use these values to generate a continuous curve in the diagram. Resembling a skewed right normal distribution. Given the observations, we expect the peak to occur around a hit probability of 0.6, which is indeed the case. If we had observed 8 hits and 2 misses, it would be skewed more to the right. And if we had observed 1 hit and 9 misses, it would be skewed to the left. Now let's imagine we have a total of 100 observations with 60 hits and 40 misses, which changes alpha to 61 and beta to 41. As expected, the maximum remains at 0.6. However, the beta distribution becomes noticeably narrower and more peaked. This also aligns with our expectations. As the number of observations increases, our certainty that the hit probability is 0.6 grows in accordance with the law of large numbers. A certain margin of flexibility remains on either side of this peak value, but it is now in a much more confined range. If on the other extreme we had 0 observations, causing alpha and beta to both equal 1, the result would be a flat line depicting a uniform distribution where all hit probabilities are equally likely. Moving on to the cumulative probability function. This is the tool we would use to calculate actual probabilities. Remember, in continuous probability models, single values inherently possess a probability of 0, so lowercase f has no probability meaning. Integration is essential for deriving probabilities. In terms of the formula, the only alteration is to insert 1 or true to represent cumulative. By doing so, we can determine, for instance, in the case of observing 6 hits and 4 misses, the likelihood of theta being smaller than or equal to 40% amounts to 9.9%. Conversely, the likelihood of the hit probability surpassing 70% is around 1 minus 0.79 equal 21%. Obviously, I can also chart the cumulative distribution function, which I will do real quick. And we will get back to it in just a moment. But before we do that, let's take a look at the capital A and B in the Excel function. This convenient feature allows us to adjust the bounds of the beta distribution. Recall that we initially worked within the bounds of 0 and 1, since we are dealing with proportions, rates, or probabilities. However, certain situations might necessitate altering these boundaries. For instance, the lower limit could be 10% and the upper limit might be 50%. Capital A and B permit customization of these bounds and adapt the beta distribution accordingly. The same, of course, applies to the cumulative function. Omitting these values sets the default bounds 0 and 1, as we've already seen. Lastly, I'd like to introduce the inverse beta distribution. For illustration, I've moved the chart of the cumulative probability function up here to remind ourselves that the inverse function uses a value from the vertical axis and obtains the corresponding value on the horizontal axis, which represents the hit probability theta. The formula to use here is beta inf, with the cumulative probability as the argument and alpha and beta as parameters. To exemplify, we can be sure with, for example, 90% certainty that the hit probability theta is not greater than 0.759 when we have observed 6 hits in a total of 10 trials. To summarize, the beta distribution can be appropriate when you want to estimate the likelihood of values that are confined to the interval from 0 to 1, such as percentages or probabilities. To apply the formula, you need to determine the parameters alpha and beta. Based on empirical observations, a simple rule is alpha equals the number of hits plus 1, beta is the number of misses plus 1. In Microsoft Excel, you can use the functions beta dist and beta inf in support of your calculations. That concludes the video on the beta distribution. I hope you found it useful and I thank you for watching.